Okay, last example of this section. A rigid rod of length 10 is attached to a circle of radius 4 at a point A. The point B is able to freely move along the horizontal axis driving a piston. If the wheel rotates counterclockwise at 5 revolutions per second, find the point of location B as a function of time. And then the detail, the second question is, when will the point B be 12 centimeters from the center? So here's what we need to understand. This is kind of hard to visualize, just like the last one, because things are moving. So I'll show you this in a second. But this point, this attachment point, is rotating around this circle. And what happens is then this piston moves in and out. So let me show you what this looks like when it is in motion. So I'm going to let it rotate, and you can see what happens. So the rod that connects to the piston is a fixed length. So as my wheel rotates, that rod draws my piston in and out. This is a very common action in all sorts of rotating equipment. Pumps work like this. Your car engine has, well, some of them have something, an actuator that moves like this. This is how we turn rotary action into linear action. So what are we actually doing? Well, what we are actually doing is we are writing the equation that describes the motion of the leading edge of that piston. So the edge that is closest to the wheel. Okay? So what we are doing is we are writing the equation that describes the motion of this point right here, this point. Okay. So let's bring up Desmos alongside our working space here. And I'm only doing this so we can visualize, okay? So when we're going to make a little table of the position of that piston compared to my angle of rotation. So theta and location. So we're going to just call that X. Okay, so we can see that when my angle is 0, then my piston is the full length of my rod plus 1 radius away from my center. So my radius is 4, my length, so that's 4 plus 10 is 14. Now, we can do pi also. Pi is pretty easy. Let's see if it'll let me do this. No, okay. So if I make that guy be pi, well then it's actually the full length of my rod minus 2 radii, which is 10 minus 8 is 2. I would like to take a look at pi over 2, but that's a little more complicated. So I'm going to sketch that out, and actually, let's see. Let me do it this way. All right. So let's take a look at this. When my angle is pi over 2, can I figure out that distance? Well, sure I can, right? Because, look, I've got a right triangle here, and I know this length is 10, and I know this length is 4, So this length is going to be the square root of 100 minus 16, which is the square root of 84. Oh, which simplifies. Let's see. So that would be 2 square root 21, and that's as far as down as we can go. Okay. That's really, so we see how to do that. But what if I'm not at a nice pi over 2, right? Or pi over, I want to be able to do this as a function of theta, any theta. Well, so let's go back up here to my sketch. And let's drop a vertical, and let's just make ourselves a right triangle. Now here's what I know. Remember, I know this, I know the coordinates of that point. That point is 4 cosine theta for sine theta. So I could almost get it because I've got this distance here is 4 cosine theta. If I can just get that distance, then I'm in good shape. Well, I can do that, right? Because this is the square root of 10 squared minus the y-coordinate, which is 4 sine theta squared. So my x-coordinate as a function of time is 4 cosine theta plus the square root of 100 minus 16 sine squared theta. Now, what have I not taken into account? I need to talk about my period because I've assumed I make 1 revolution a second in this equation. This tells me I make 5 revolutions every second. So I need my period. My period needs to be 1/5, which means my internal multiplier needs to be 2 pi divided by 1/5 or 10 pi, which means that the equation that describes the position of that piston is equal to 4 times the cosine of 10 pi t. So what I'm really saying is that my theta, my angle, is described by the function 10 pi t plus the square root of 100 minus 16 times the sine squared of 10 pi t. So this is the function that describes the position of my piston. That's pretty. Okay, that's part 1. Now let's do part 2. Part 2 says, when will the piston be 12 centimeters from the center of the circle? So remember, this is my point B. Well, we write here that 12 equals 4 cosine 10 pi t plus the square root of 100 minus 16 sine squared 10 pi t. And so this is an equation that involves a square root. We remember from previous classes that the first thing we do is isolate that square root. And that then will equal the square root of 100 minus 16 sine squared 10 pi t. Now we're going to square both sides, but remember this is a binomial. So this is 144 minus 96 times the cosine of 10 pi t plus 16 cosine squared 10 pi t equals 100 minus 16 times the sine squared of 10 pi t, which looks really ugly, but let's not panic yet. Let's pull everything over to the left-hand side. So we end up with 44 minus 96 cosine 10 pi t plus 16 times the cosine squared of 10 pi t plus 16 times sine squared 10 pi t equals 0. Oh, this is looking promising. Let's put these two in parentheses and factor out the 16. We get 44 minus 96 cosine 10 pi t plus 16 times the cosine squared of an angle plus the sine squared of that same angle equals 0. This whole bit here goes to 1. So I've got 44 plus 16 is 60. 60? 60. Let's move the 96 cosine 10 pi t over to the other side. Divide through by 96. We get 60 over 96 equals cosine of 10 pi t. Let's reduce that 60 over 96. More accurately, let's ask Desmos to reduce that 60 over 96. It's 5/8. It's a much better number. Okay, and we want to know when, this just says, when is my piston more than 12 centimeters from the circle? And it doesn't really give me any boundaries, so we're going to have to find all of them. Okay. Remember our period, the period of this function is 1/5. That means our times will repeat every 1/5 of a second. So I'm going to do this a little bit differently than we normally do. And I'm going to show you, because we know our period. So that makes life a little simpler. So here's what I'm going to do. I know that 10 pi t is going to be equal to the inverse cosine of 5/8. And I'm going to get two options. So I'm going to go ahead and do my theta. So let's back up a second here. Let's go ahead and let my theta equal 10 pi t. So I'm going to find my first theta is the inverse cosine of 5/8, which is going to be, whoops, and let's make sure that we are in radians, and we are, so we're good. So my first theta is 0.8957. All right, on the unit circle, that puts me, 5/8 is a little bit more than half. Whoops, that's wrong. That's about right. Okay. So 0.8957. The other angle that has the same cosine is this one, which is 2 pi minus 0.8957. So 2 pi minus 0.8957. So my other theta is 5.3875. Okay, now I want to turn this into times. So remember how this works. My time is each theta divided by 10 pi. So my first time is 0.8957 divided by 10 pi, which is 0.0285. And my second time divided by 10 pi is 0.1715. Now, why do I wrote down the period, and I made a big deal about the fact that we knew the period, and that's because this is plus 1/5 k. So in other words, each cycle I hit the target position of 12 centimeters twice. The first time is at 0.0285 seconds after the cycle begins, and every 1/5 of a second thereafter. And the second time is 0.1715 and a 1/5 of a second thereafter. So we can do this. Okay. I hope this makes sense. Reach out and let me know if you have any questions, and I will talk to you again soon.